There is a technique for finding formulas for something like 1 squared plus 2 squared plus 3 squared plus up to n squared, or any power, provided we know the formulas for the same sum with smaller powers. So for instance, let's say I already know that 1 plus 2 plus 3 up to n is n times n plus 1 over 2. And that's something I know, and we've derived that one before. I want to show you how that formula could be used as a step in in deriving this formula. And here's the way it works. So in order to do it for, we're doing it for squares, we're going to first work out the difference between n cubed. So if I'm doing it for squares, we take 1 power higher, minus n minus 1 cubed. Now when you raise n minus 1 to the third power, there's a general rule about raising a binomial to the third power. It's going to be a cubed plus 3a squared b plus 3ab squared plus b cubed. These coefficients 1, 3, 3, 1 came from the third row of Pascal's triangle, where every number is the sum of the two numbers above it. So when we apply that to n minus 1 to the third, it's going to be 1 n cubed plus 3n squared times negative 1 plus 3n times negative 1 squared plus negative 1 to the third, which becomes n cubed minus 3n squared plus 3n minus 1. And then when I distribute through this minus, I get minus n cubed plus 3n squared minus 3n plus 1, and these cancel out. So I now have this sort of identity. 3n squared minus 3n plus 1. Here it is again. So n cubed minus n minus 1 cubed is 3n squared minus 3n plus 1. Now I'm going to take this formula and I'm going to plug the number 1 in for all the n's. Now I'm not going to actually multiply these out. I'm going to leave it as 1 squared and 1. Then I'm going to plug 2 in for n. 2 minus 1 is 1. And I'll plug 3 in, and then I'll jump ahead to the general case. And I'll say dot, dot, dot. Then I'll put n in. Now if I add together all these equations, what ends up happening is that the minus 1 cubed cancels out with the 1 cubed, and the minus 2 cubed cancels out with the 2 cubed, and basically everything ends up canceling except for n cubed. So the left side is just, what I'm doing is I'm adding these together. So the left side is just n cubed. But the right side, see, this is 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared. So it's 3 times 1 squared plus 2 squared. This is convenient because this is the thing I'm trying to solve for. We also get, I noticed somehow these minuses became pluses. I also get minus 3 times 1 plus 2 up to n. And all these 1s, there's n of them, so it's plus n. Now, since I'm trying to solve for this thing, I'm going to move these guys to the other side. So now I have n cubed, I'm going to add this. It's being subtracted. So it's plus and here I have plus n. I'm going to subtract that, so it's going to be minus n is equal to 3 times 1 squared plus 2 squared. Now, we have a formula already for this. It's n times n plus 1 over 2. Now this is going to require common denominators of 2. So 2n cubed over 2 plus, I'm going to multiply this out, 3n squared plus 3n over 2. And this n minus n is going to be minus 2n over 2. We get the common denominator. Okay, so common denominator of 2, so I get 2n cubed plus 3n squared plus 3n minus 2n is just plus n. Divide both sides by 3, and this becomes a 6. And we're finished now. This is the answer. 2, 3, 1. We have 2n cubed and if you notice, I can factor that, and I could even factor it more to get the formula that we're all familiar with. So that's how that works, and this can also be done if you want to know the sum of the cubes formula. You can start with n to the 4th minus n minus 1 to the 4th and do the same process.